So good. So tonight we're actually doing another members presentation night. We'll be doing 4 speakers. I've got a couple of two in person, 1 pre-recorded, and 1 person doing a remote Zoom. So it is a bit of it's certainly a hybrid meeting because we're trying all methods to see whether there's any problems. So Marcus, we'll do yours first because that way it'll be easy to do the other ones afterward, I think. So come on down, Marcus, and you can tell us about your ideas.
Okay. All right. Cheers. Thank you. I'll just get my screen up again.
Saw it a minute ago. Yeah.
Where are you, Marcus?
I'm up in Musselbrook, actually, the Hunter Valley.
Oh, you got the shirt. Yeah,
Yeah, you can read that.
Yeah, good on you.
Yeah. Yeah, I'll hold up.
We had it a minute ago.
Yep. Screen, entire screen, start. All right. How's that?
Okay. Yep. Yeah, we can see it now.
Okay. Good stuff. All right. This might be a bit wordy. I'll just smash through it.
I think that's the whole screen. Yeah. So I think we should change the notifications.
If you cut the chat out.
All right. So people, ideas, and projects. That's how I think we can go about developing the space frontier. That's my dream. So there's three steps. The first step, which I'll get to at the end, is the idea to have a space construction school or even just an event. And that would engage people and obviously start to develop ideas and get people talking about the ideas to build a community. And get into ideas. The ideas is obviously there's a lot of research to be done. There's still certainly literature reviews and understanding what can be done, and then from there to work towards projects. I think it's good to work on projects on Earth to learn the engineering skills. So labour hire and project development for construction projects on Earth. It takes us from ideas to projects. And then in the long term, step 3, I'd like to obviously work on space construction projects. There's all sorts of ideas, which I'm sure you guys are aware of, preaching to the choir, in low Earth orbit, lunar bases, L5, etc. And that gets us from projects that really bring the benefit to people. That's the future for life. So to start with people. Hi, I'm Marcus. I've met some of you before, and I'm a sci-fi nerd, as I think some of us are. I am a cook by trade. I used to work just down the hill there in the other side of the harbour in a Key restaurant, and I always had a dream to have a space restaurant in zero gravity. Try the soup. So I studied as an engineer. I did chemical engineering at Sydney Uni graduated in 2018. But I've been working recently in engineering, but not as an engineer, as a welder's assistant and rigger. I'm working at the power station up here in Musselbrook. So there's not much of a future for these power stations, but it's good. There's good engineering skills to be had there, and it's good experience, I think. So other people, obviously, there's the Sydney Space Frontier Society. Thanks for giving me the opportunity. It's good, good opportunity. And the vision statement, the vision of people living and working in thriving communities beyond Earth. I think that's a powerful vision. Other people involved are especially the younger workers at the power station, being as these industries don't have a huge future. There's graduate and the people at the power station obviously aren't very interested or don't really understand the potential for space. But there's university graduates, space engineers, and the broader space community. Other people, the larger organizations, obviously the space agency, universities, and large companies the companies probably don't really understand, but they've got the capabilities to do these large projects. People ultimately is about all mankind. And with the space frontier, it creates opportunities for everyone. Yeah, so we don't have to fight over what's the small Earth. So that's the hope. Future generations and beyond Earth, I don't think there are any people. Certainly not. We haven't found any in this solar system. But yeah, what Al Globus quote, he said, bring life to space and bring space to life. So that's, yeah. So from people to ideas, this is a bit of a brain dumper. Probably won't go through everything, but I think, yeah, important thing is like political balance to get things done. In any organization, any community, it's important to get things done and also to look after people. So I don't know, I spend too much time on the internet and there's a lot of political division. So to try and bring a community together. Yeah, there's a bit of politics there, but the Elon Musk, he's a political divisive character, but yeah, the way he does his approach to engineering, which is to really question things and simplify. There was something in the news about potential for more launches from Australia, from America, the Technology Safeguards Agreement. So that was another idea that might open potential. So engineering is a real adventure, and you've got to go quite deep. You got to really take on the challenge. It gets quite difficult. So some of the projects at the power station, like it's not always fun. It's a bit of a challenge, but step by step. All right. So yeah, some of the skills or the basic training that you do at the power station just to get on site is a confined space ticket and a work at heights ticket. I didn't. I was a bit surprised when I finished university trying to get a job that this basic training wasn't provided. Well, I came out of university with a lot of knowledge, but they didn't have the qualifications to do basic work. So yeah, those tickets are pretty important for construction work. And then there's further training, rigging, cranes, the work platforms, the picture on the right. Working on those basket cranes. I've done a bit of work in them. It's quite fun. And then other space related training would be pilot training and range safety for even model rocket launches. And then there's a few business models there, obviously. Yeah, some of you would know more about that than I do. But even large projects on Earth, if we want to build thriving communities in space, we can start perhaps by building some thriving communities on Earth. An example like that NEOM project in Saudi Arabia they're thinking about. That's just some ideas, and there's plenty of future business models for to develop for space. So yeah, the projects in particular, how I see, to build a company from scratch, and I might not be the one to do it necessarily, but I'd like to share the idea. If anyone, it's good to put the idea out there, I think. So the long-term projects, and there's plenty of projects from O'Neill Systems and Al Globus in particular was one. But in the medium term, to develop, if you've got a team of people to develop the engineering skills, it's good to work on projects on Earth, construction projects. To have a team of people doing that, to raise the money and to develop the skills. And if you have a productive industries on Earth, you can have people working. You can keep a team together. I think that's the idea. And then in the short term, I'd love to, have a space construction school and invite people. And I think the first thing, the simplest thing would be to do a one-off training event. So an event in summer for students and for for anyone really who'd be interested, invite people. And the program, maybe a 3-day program. Day 1 would be a introduction to space history and potential, future potential. Day 2, good to focus on real construction skills, confined space and working at heights training. So confined space, if you don't know, is to go inside tanks or pipes, where often the main risk is the atmosphere. So you need breathing apparatus, or and they use gas monitors, and so it's quite dangerous to go inside a tank where the oxygen might be depleted. So that's it's important training. I think it's relevant in particular to doing space walks and same sort of skills and processes. Obviously more complex in space. And then day 3 on a training course would be figuring out how to what business models, like you can focus on designing space stations and whatnot. That'd be a good, well, that'd be very interesting, I reckon. So it's an event management problem. I think if anyone would be interested, I'd like to, you need a team of people and a venue and a date and a program. If anyone would like to help, I'd love to talk about that. That'd be great. Anyway, that's all I've got. That's my Instagram. I've got a website, but there's nothing on it yet. I've got the domain name registered, but don't have a website yet. So I've got an Instagram page. It's just got some ideas. And thank you. All right. Is there any questions?
Just curious, have you seen the Apple TV series For All Mankind, the most recent season? No, I haven't. You might find it quite inspiring, because it's much more about the worker bees that will be going to space eventually.
It's the one on Mars though, where they were doing the Mars.
It's about settling Mars, but it's about it's about it's
realistic?
not all about the astronauts anymore. It's about the people who have to build things.
That's a good point.
And mine and that kind of
There's a lot of ethics issues in that last 4th season.
Yes, but so it's a really it raises a lot of the questions that you were just bringing up.
So where do we see that?
It's Apple TV.
Apple TV, For All Mankind.
For All Mankind. It's on its like.
Yeah, that'd be a good one. Is that realistic? Is that a realistic science fiction? Realistic short near-term sci-fi?
Yeah.
Yeah, sounds good.
And it's kind of an alternate history.
Yeah, it's an alternate history, and I think that was still set in the early 2000s. So he hadn't actually got to that.
Yeah,
it's still
I don't want to give too much away, but so
yeah, spoiler alerts.
Yeah,
I'll look it up.
No spoilers.
Lou, you've got a question?
Marcus, in your section about ideas and projects, you got one point was avoid government. Now, talk to that for a minute. I mean, if you avoid regulations, you get a mess usually. So, basically, what is your experience with that? Things that you want to avoid. I mean, government.
Yeah, actually, that was something I wanted to mention. Is I went to Adelaide to the Space Discovery Centre, and I guess it's a bit political. I guess I'm revealing my politics here, which is there was something in particular there that there was like a survey on a screen, and the question was like, what should be allowed in space? Should people be allowed to settle on the moon? Should companies be allowed to operate space stations? Should the government be allowed to settle Mars? And it just seems like I think the government can only regulate. The government can't actually drive anything. Obviously you need government, but
dampen down exploration.
It takes a small team of people. You don't need a it's got to be driven by people.
I see what you're saying. It's like they dampened inspiration, but eventually, unfortunately, we need them. Otherwise, it gets a big mess, doesn't it? Everybody
I
getting
think he
in.
means
Oh yeah, no, regulation is important, but I don't think regulation drives, and that's the role of government's to regulate.
Yeah.
I don't think, I don't think the government should be really trying to pay for everything. But NASA did well in the '60s in America, sort of only with the residual war from World War II, the residual energy, and so it was the JFK regulated that and put that energy towards something positive. But the
Okay,
energy doesn't come from the government originally, I think.
yeah, I understand what you're saying. Yeah,
But,
inspiration,
yeah.
government regulation later. Yeah.
That's just
Okay,
it's a political opinion. I shouldn't. But yeah.
Okay, John, you're at the, okay.
Can you hear me from back here? So,
Yes.
well, I hope so. Well, all right, I guess this is getting political. I can't help myself, but I once heard a farmer talk about his experience that he would get up in the morning, check out what the Bureau of Meteorology said, and then make a decision involving tens of thousands of dollars as to whether he was going to harvest his crop or not. And so when I hear that government doesn't create value, I guess this has got nothing to do with space, but I can't help but observe that sort of contribution that government makes to the economy and what is happening. So that's got nothing to do with space. So I acknowledge that, and probably what you said has not got a lot to do with space. But okay, regulation, oppressive regulation, it's bad, but there are places where the government really does help things along. So,
Yeah, absolutely. I guess I'm saying like it's probably more like even an urban thing. Don't the to go into the city, like to go to space is like it'd be good to be able to go to rural, to remote areas first. So you don't need a big, I don't know, you don't need a big democratic consensus to be able to develop the space frontier. I think it takes small teams, but certainly there's resources. I'm not in favor of abolishing the government. I should say that. But yeah, cool.
Right, we've got time for one more question because we've got to have to rotate the speakers through. So has anybody got anything else they want to ask?
Yeah.
Janine? Yep.
Had you thought of collaborating with the Defence Department with submarines? Because living on a submarine is pretty well parallel to living on a spaceship, and they can use the underwater experience in terms of spacewalking. But the other thing too was, I think it was Glencore have a rare earth mining site somewhere in central New South Wales, which was an open pit and is now underground, which would be a very good site for constructing habitats within the wall, because they're obliged to rehabilitate the site, and they were interested in that. So had you thought of doing a collaboration with a mining company as well?
Yeah, absolutely. I think it's like the planning to work with experienced underground mining planners, like the really experienced trades and operators who plan projects underground. I think that'd be a huge resource. Like if you were planning lunar bases with tunnels, you'd really want their input because the experience is incredible. But they really know how to do things. It reminds me of that, the movie Armageddon, where they've got to drill on an asteroid to blow up the asteroid because it's coming towards Earth. And so they get Bruce Willis, who's they're working on oil rigs. They need the skills to be able to achieve a project like that. So getting those skills from the mining industry, those skills certainly exist. I'd love to connect with to plan projects. I think that's the way to do it. All right. Yeah, thanks for the opportunity.
That's fine, and I'm sure some of the other NSSA people will probably talk to you later on about it, Marcus. Thanks very much for your ideas, and there's certain things we can play with there, I think. Okay, so I'll just change this so we can get that. Tony will be the next person. Trouble with going to
Share that.
I feel like you're all thumbs.
Because you got to turn it on and then push the volume down. Bloody thing.
I'm a bit worried
My
about
logic
losing the
was like, you should be able
screens.
to bloody turn the volume down before you can put it on.
Just play.
I was trying to look up the rare earth metal place for it. Because I've already laid.
So we need something different to this. This isn't the solution. I'm just thinking it's going to fall off all the time too.
It's gotta take holding.
Okay, it's got-
You can just see ours. Yeah, okay. Can we kill the,
Just put it to the, just by your.
yeah, we can't do that.
Oh, symbols.
No, you can get rid of, just press the one on the left or move it over to the side.
Good. Okay. This is going to be a pretty simple one. It's basic satellite communication. I gave a talk with Killian, we talked a while back about software defined radios. That's a small part of this. This is the more broad overview. In general, spacecraft is a space satellite system consists of two parts, right? And the two parts are the bit that's up there, it's the satellite, and the bit that's down here, the ground station. And it's important to remember that you need both of them. They're 50-50. It does not work unless both of them are working. You might as well launch a house brick. Okay, so we'll start with the bit up there. Usually, for the purposes of operation in Australia, it'll be something like a picosat of some sort, like a CubeSat, maybe something a bit bigger, like to see as time goes on. And the downlink signal is transmitted usually by some form of linear antenna, which will mean that the signal is either linear or circularly polarized. Okay, and I'll explain what that means in a minute. The spacecraft isn't usually, not always, but it usually isn't directionally stabilized. If it's not directionally stabilized, you have no way of knowing which way up it is. If you have no way of knowing which way up it is, you don't know what orientation the antenna is with respect to the ground, and therefore you don't know what antenna orientation that your antenna on the ground has got to be to receive the signal. The best way then is to use, and as it passes, if it is organized, usually is aerodynamically stabilized in some way. As it passes the ground station, what's known as the chirality changes. Now that's a word you won't have seen before. Some of you, many will, but some of it won't. And I'll explain what chirality is. If the signal is circularly polarized, then the plane of polarization is rotating with respect to the point of from the point of view of the transmitter and the receiver. Okay, so the transmitter there, if you look at it, has transmitted a signal which from the point of view of the transmitter is rotating in a clockwise fashion. Okay, but on the other end of it, on the side facing along the z-axis, it will appear to be going the other way. Okay, so that is known as the chirality. It's a chiral rotation. And it affects the way, because of the way you've designed your antennas, it affects the way your antenna works. Your antenna has got to be designed to receive one chirality or the other. So we call this right-hand circularly polarized or left-hand circularly polarized. Okay. So just so you know about chirality, that's important. Okay, the bit down here. Okay, so now that's going to affect us here on the ground. All right, so this is an approximate example of an antenna that you could be using. You notice that there's a spiral wire there. That spiral wire is designed to receive a left-hand circularly polarized signal. You can tell by the spiral of the antenna as it comes down to the reflector of the back there. But it can either be a dish, conventional, paraboloid, or what's called a yagi. Yagi is a series of discrete receiving or directing elements leading towards a receiving element in the bag. Okay, the advantage of circular polarization, it doesn't matter which way the spacecraft is oriented. Okay, so you can receive the signal no matter what.
Oh, that's good.
That's very good. That's a very handy thing, yeah. So there's no need for spacecraft directional control, and there's no need for any directionality on the antenna on the spacecraft, which means it's a simpler, lighter, cheaper spacecraft. And the most expensive thing to do, single thing to do, is launch the thing. The less complex it is, the better it is for it to be simple. The cheaper it all is. Okay. It can use either linear or circularly polar. Linear is where you've got a simple transmitting wire, where the oscillation is in one plane. But the receiving antenna on the ground is going to be able to receive any orientation. As long as we can receive a linear signal with a circularly polarized antenna, or with a circularly polarized antenna, providing we've got sufficient sensitivity and that these days that's not difficult. Okay, the disadvantage of circular polarization. As the spacecraft passes the ground station, if it's a stabilized spacecraft, the chirality changes and you've got to switch the chirality of the receiving antenna. And this is not easy to do. Well, actually, you've got to know to do it, and it's got to happen very suddenly, and it can interrupt communication. So we need some kind of chirality switch, which can be done. There are numerous examples of them around. Okay. I won't go into that now, that's just too much detail. The other thing we've got to take care of is Doppler shift. Now, what's Doppler shift? Well, the speed of a spacecraft in low Earth orbit with respect to the ground is of order about 8 kilometers per second, maybe a little bit less, about 7,500 to 8,000 meters per second. That's a significant speed, and it alters the apparent signal frequency. Depending on what the baseband frequency is, that can actually take you right out of your assigned channel. Okay, the worst case example is when your spacecraft comes over the horizon, when you first acquire it, it's at its maximum Doppler shift. And at say at 70 centimeters, that Doppler shift is about 11 kilohertz. Yeah, 11 kilohertz. That's quite a lot. And you've only got about a 30 kilohertz bandwidth. So that's 15 kilohertz either way. So a significant portion of the signal is outside your assigned band. Okay, light equation, sorry. This is the only one I'm going to do. How do we calculate it? We've got a frequency that we receive. I'll just show you the others. The frequency that we receive, we've got the speed of light. C is just the speed of light. This is electromagnetic radiation. We've got a velocity of the receiver, velocity of the source. We will assume that the velocity of the receiver is 0 because it's sitting on Earth. We measure all velocities with respect to the surface of the Earth. And so what we end up with is the initial frequency, the frequency that would appear from the spacecraft if it was standing still right next to you. But the frequency you receive is modified by that amount. And that's a graph of what I'm talking about. If you're talking about 140, 150 megahertz, that maximum deviation is of order about 3 kilohertz. That's not so bad. If it's 70 centimeters, about 430, 440 megahertz, that goes out to 11 kilohertz. That's a problem. It takes you outside your band, or right to the edge of your band. But more often than not these days, if spacecraft are using S-band, that takes you out, a deviation out to 60 kilohertz. That's way outside the band. So you have to adjust the receiver in real time in order to track what the spacecraft appears to be doing because of its velocity. If you don't do that, you get the signal just as it goes past and not either side. Now, you might have as much as a 10, 11, 12-minute window. You want to use as much of it as you can, not just this little bit here, but the whole thing. Right? So you're receiving spacecraft, you're receiving radio, has got to adjust the frequency in real time, every few seconds, as the spacecraft approaches and as it recedes. Okay, and that can be quite a lot.
Does the mouse work on the computer for pointing?
Right,
No.
yeah. Glad you said that. Oops.
Because the people at home can't see you pointing.
Okay.
Now, so the directions.
Well, the trackball should, there's, the arrow's not there.
How do I move that?
Maybe.
No, we've got a mouse over here, but maybe more.
Yeah, but how do I move that bar?
Yeah, he's moved it now, to get it out of the way.
Okay.
I need
Can you,
to,
can't you put that bar like up at the top or something?
usually before we do the presentation, you can.
Okay, I'll just add that. We'll deal with it. Okay. So now, knowing all of that, I'm going to lay out a broad overview of what the space could be, ground station design looks like. And that is approximately like this. Now, this is only a crude idea of it, but it looks like this. You've got a computer running this thing. You've probably also got a computer tracking the spacecraft, and as often as not, the same computer. The signal is received, and it received into the feeder. It's then sent to what's called an LNA. That LNA there at the bottom is a low noise amplifier. It builds the signal up, improves your signal to noise ratio. Then you go into the radio, and you see a thing there called a down converter, a demodulator, and a baseband processor. That's just the software-defined radio that I talked about a bit the last time I'm going to talk about this. And then into the computer interface, and then you do something with the data. You store it, process it, whatever you like. Okay? To transmit to the spacecraft through the interface, do the baseband processing up to the modulator at the top there, the up converter, high power amplifier at the end, and out to the antenna. So that's the basic layout of all the things you've got to do. I've said also that you've got to track the antenna. Very often, as I said, the computer that does the signal processing is also the signal that does the tracking, the computer that does the tracking. But you can have separate computers. Now, that's a good example of one. If I had lots and lots and lots of money and lots and lots and lots of space, that's what mine would look like. Okay. You've got these antennae here are called Yagis at the side. They're sort of spiky things. The dish in the middle is obvious. You know what that is. They're parallel. One of them is a transmitting. The other two are receiving. And they're phased. That means you kind of add the signals up together. It's not hard to do. You've just got to join the wires, so to speak. And then you have a computer downstairs somewhere that runs it. The one at the university, EVA's system, is not entirely dissimilar to that. It doesn't have the dish, but it's certainly got the big Yagis, that little arrangement there. And the tracking device is a combination of what's just behind the dish there and what's on the ground, that little blue object. Track. Okay. Maybe it's as simple as I could. Any questions? There we go.
Well, no, Janine has one.
Janine.
You might as well get the answer for him.
Yeah, how much? Because you said it was expensive.
Okay, right. That's a good question. It depends how much labour you get for free. That's a big part of it, because this is not trivial to put together. Okay, you don't just, it's not like IKEA, right? Okay, you set of instructions and an Allen key, that won't do it for you, right? There's a fiddle to do it. The radio equipment, if you are using the 150 meg and the 450 meg, maybe $1,000, something like that. If you're using the S-band, the 2.4 gig, it goes up to about $5,000–6,000, something like that. If you're using higher still, the price is correspondingly high. I reckon something like that, $20,000, something like that order.
Without the paying the expertise.
Without paying for
The labour.
The labour, yeah. You get high quality labour.
So I have a question then. So, I know that you are a amateur radio buff, a
Yes, I
very,
am.
very skilled one.
And indeed, I examined you.
Yes. Yes, yes, you were my marker, but what I'm saying is, there aren't a lot of young. Are you
That's-
getting,
that's-
is
that's-
this gonna be a problem?
Yeah.
Because we don't have, it's not something that's necessarily taught at university,
No.
it's taught at amateur radio.
And they're all
licensing
grey
classes.
parts like me, right? You're
Yeah,
absolutely
so
right.
they're all old parts like you and me, so, well, I am too, but I couldn't build one of those.
Yeah,
But-
we tried to get young people. One of the ways I tried was with space. You
Yeah.
know that I did the little space contact, I did talk about that to
Mhm.
the colleague. With a view to trying to get as many young people in as possible, and amateur radio people all over the world are always doing this. But the feed through from young people is still very weak. And
Yeah,
I have a feeling is that they come into a room full of amateur radio people and they see brown parts
yeah,
and they don't see too many young people. That's a problem. Yeah. But one of the best
but
ways.
it's a wonderful skill to
Oh,
have.
it's a tremendous skill, and one of the best ways to learn it is to
Yeah.
have a scientific hobby, like amateur astronomy, amateur radio, whatever you like. It's a great way to learn it. It's a great way to mentor young people through it.
Mhm.
It's a great thing to do. I wish there was more of it, but there's not. Any other questions? Okay, one of the rules.
Get that bar out of the way before you share it.
If you click on more, it may well give you an option to disappear the bar.
That's a good point. Yeah, I'm just,
Usually you can hide the bar.
Yeah.
It's still not someone controlling.
This-
We just.
Oh, it's your.
Yeah.
Oh, well, there we go.
You on?
Yep.
Yeah, okay, so, yeah. Sorry, I think we tend to take our own sun for granted. I personally have thought over the years a lot about the planets and their various other solar bodies, but not the sun. I just accepted that the sun came up in the morning and it's this unfathomable object in the sky. And similarly, I think with spacecraft, and this came to me when I started looking at the OSIRIS-REx program last year, we get excited about the sexy stuff of the manned, understandably, of manned spaceflight, but we tend not to focus on the myriad craft that have done and are continuing to do astonishing things as we speak now. So I thought the Parker Solar Probe, I just brainstormed this, was kind of combine both these, the mystery of the sun and then the complexity and the subtleties of spacecraft. So where am I? When I'm in business here, just
use the arrows.
stand there like that. So why Parker? So let's understand more about this giant sphere of fusion upon which all life depends and from which our solar system, we all came from this great thing here. Coronal bursts, solar flares, mass ejections and other seething maelstroms disrupt our world and have the potential to be catastrophic in their effects. We've seen that a couple of times just in the last century particularly. Can we improve predictions, allowing time to take preventative actions? Looking at the probe's origins, it was conceived, well, the idea of looking more closely at the sun was conceived by Dr. Eugene Parker, who was at the University of
Chicago back in the 50s. And ultimately, this came to fruition through the Goddard Space Flight Center and Johns Hopkins University in much more recent times. And was finally launched after many years of development in 2018. And for those of us that like rockets, it was a Delta IV Heavy with an upper stage. I think the upper stage is a solid from memory, Wayne. 685 kilogram, and again touches on something else that we don't often think about. These things are really, really large. I mean, this is a 3/4 of a ton object, which we've launched into the inner reaches of the solar system. Similarly, when we think about the Perseverance rover, that was a 2-ton craft that's still to this day just roaming around doing very, very important research on Mars. It's scheduled to end in 2025, and when I Wikipedia'd how will Parker end, it's a bit of an unknown. Nobody quite knows whether it will become just an inert object or whether it will ultimately perish inside the sun. But certainly by 2025, its useful life will have disappeared. Here's Dr. Parker visiting his dream during the assembly stage, and he lived to be at a grand old age, and I think passed away in 2022. So he got to see the launch and saw the evolving trajectory. Parker was launched with a sun-centric elliptical orbit with a lot of help from Venus. When the craft was first conceived, it was designed to fly out to Jupiter and use the gravity assist from Jupiter to ramp its velocity up. The problem with it moving out to the Jovian system, of course, is you can't rely on solar panels, so that meant a thermoelectric generator on board, and which significantly affected the cost of the thing. So Venus was determined, 7 gravity assist flybys of Venus to achieve high speed and progressively closer approaches to the sun. So this thing whips around. There's an animation coming up soon, which will show you how that works. Total of 24 elliptical orbits with diminishing perihelion and closest approach. So as it's getting faster and faster, getting closer and closer to the sun over a number of years. The closest approach to the sun is only 6.2 million kilometers from the center, which is about just under 10 solar radii from the sun center. And throughout, it actually flies through the outer corona of the sun. It's the fastest man-made object that we've built. It's currently doing, or it's at its closest approach, it's doing 698,000 kilometers per hour. I just looked at the last presentation where we talked about 6,000 or something, 7,600 meters a second. This is now doing 192 kilometers a second at its closest approach, which is really fast. It's a fun fact. Even at that speed, which is 0.064 of the speed of light, 7,000 years to reach Alpha Centauri. So unless there's some radical breakthrough in quantum physics, and probably there will be at some point, we're not going to see interstellar travel, certainly in my lifetime, in our lifetimes. But I thought that was an interesting observation because we tend, we talk, there's Alpha Centauri, it's only 4 1/3 light years away. At this speed, 7,000 years to get there. So this is the orbital dynamics, and I stand in awe of the people that feed this information and decide this is the way to do things, because Tony, it's a bit like your radio mathematics. It's now way beyond me, this sort of stuff. I understand the principles, but I'm in awe of how people conceive of and calculate these gravity flybys with such complexity. So you can see the sun at the center, and then the orbits of Mercury, Venus, Venus, and Earth.
It's getting closer and closer.
Getting closer and closer.
It's going to be 24.
So the instruments, essentially four instruments: electromagnetic field mapping, which you'd expect, looking for particles, electrons, protons, and ions. Energetic particles, alpha particles, electrons and protons, and it's doing some optical imaging as well, which is where the nice pictures come from. But what about the heat? Here's this thing, this 685 kilo minus some propellant usage, getting closer and closer to the sun. It's getting hotter and hotter and hotter. So it's shielded with an 11 centimeter thick carbon composite heat shield to protect the instruments and the control systems from temperature. because it's getting really, really hot out there. The thermal load of the closest approach is 650 kilowatts per square centimetre. When I went to university, we used to use a 1 kilowatt bar heater to cook our toast on late at night. So 650 kilowatts per square metre. Imagine 650 single bar heaters a metre away from your radiating. That's the sort of heat load that's Parker is experiencing. It's 475 times the intensity of this solar radiation in the infrared, I guess that means, at the Earth's surface. So it's hot. The spacecraft's autonomy constantly ensures the correct orientation. If that heat shield is not oriented correctly towards the sun, this is going to cook really, really quickly. That means, of course, regular signal loss, because the thing's turning around, the signal is going to get messed up, and there'll be periods of time where it won't be optimum signal response. But this craft has, because of this need to constantly orient its heat shield, it's setting standards of spacecraft autonomy. Wait, well, this should play on this, should it? On the trackpad somewhere? No. If I just do, oh yeah, there's a cursor there. Yep, I got it. Yep. So this.
Oh, we got the cursor.
Let's see if it does it. But this really is just a synopsis of what I've been talking about.
You might have to do you have to reshare it.
Well, that was a surprise I wasn't expecting, wasn't it?
Yeah, well, we live and learn.
It's because it's opened up YouTube in a different window, so you have to go to the.
It's really just a snazzy summation of what I've tried to explain.
Right. Yep.
No, it's not weird.
Oh.
Modern technology making life easier.
There you go.
They can see it there.
They see it at home.
I'll stop it. Now, I don't know whether you can see it or not, can you?
No, let's not waste time doing that one. It's just a cool little video talking about temperatures and distance from the sun.
Well, ask Wayne to put it in the next bulletin.
There you go.
Oh.
So that's what I found out about the Parker Solar Probe. Hope you've enjoyed it. Thank you.
Yeah, that's great.
Done.
Questions?
Can you share that link in the chat?
That's a good idea. Maybe.
Look, I could ask a question. I don't know if anyone would know, but those materials, that heat resistant material, are there specialists? Is there a specialist company place in the world that people that do this, or is it just done wherever it's needed? Don't worry if nobody knows. I'm just curious. It's an amazing skill.
It's something like Rolls Royce because they encapsulate the
What was that? Lou?
radioactive materials.
Oh, so I'm amazed by those materials, how heat resistant they are. You know, the carbon. Is there a specialist place in the world, a specialist country who does this, or is just done by the nearby company wherever it's needed? That's just.
I really don't know. I would imagine that a number of organisations around the world do refractories, very sophisticated, lightweight refractories, which essentially is what this thing is. I mean, if you think back to the tile development on the shuttle, that was in a similar vein. That was,
Got one hold the cube by the corners and it's red hot inside.
yeah, that's like the thing. Yeah.
Yeah, what's the period for the orbit? How long does it take to go around the sun?
I'm not sure. It's a long orbit. It's a long period because it was only doing 7 or 14 revolution elliptical orbits in over 7 years.
7 years.
So it's a long period.
Isn't that 6 months or something?
Yeah.
Okay.
Yeah.
So I'd assume that by the time it gets out to Venus, it'll be travelling a lot slower and then winds up as it goes.
But so what about
Yeah.
the solar panels? Well, the heat shield is in the way, then the solar panels can't be gathering electricity, can they? Is that right?
Probably right, yes.
So like, I would imagine once you get far enough away from the sun, you can pivot around the other way and once you put the solar panels towards the sun. So
Yeah, the graphics that I found on the craft didn't really focus too much on the panels, and I just assumed that they were relatively small to avoid that very problem, because otherwise you'd fry. You know, the heat shield is relatively small as well because it's shielding the instruments and the control system.
But the other thing is, you know, if the instruments want to detect something, I mean, obviously they can detect the environment.
Yep.
But they can't see through the shield to see what the sun's actually
No,
doing.
they can't. No, they can't. No, they can't.
Because it means that look, that be probably burn up quickly.
Well, I could imagine there might be something on a boom that you extend past the heat shield, and it then looks down and it's the part that's exposed to like the full heat of the sun. You know, you could imagine it doing something like that.
Yeah, the little animation showed it was quite useful. One of the things it showed at the end was the increasing temperature, and at the point of perihelion, the craft is enduring a very, very high temperature. I think it was the order of a couple of thousand Fahrenheit.
I put the link in the chat there, so they should be able to do that later. Which is good.
For the reasons you mentioned, Alan, Parker Solar Probe doesn't have any images on board.
Right.
Because when you get too close to the sun, when you get too close to 10 solar radii, the imaging plane gets entirely burnt.
You would think so. Yeah.
So they quite deliberately have the shield there so as to prevent the particle instruments from getting too hot.
Okay.
The magnetometer from getting too hot. That's the other thing that's out on a boom.
Yeah.
Everything else is behind the shield. And the reason for that is just because electrons, for instance, at this sort of, well, anywhere in the solar wind closer to the sun than Earth, go at 1,000 kilometers a second.
Yep.
The spacecraft goes perhaps at 30 kilometers a second. So the electrons come to you from wherever, from behind the heat shield. And the ions don't necessarily. So you have to be careful, clever, to try and actually see the ion beam coming from the sun.
I think when you take all of these things into account, it's quite remarkable, isn't it, that you can build something that will survive that sort of environment, and not only survive, but to do it repeatedly. Because I think there's about, let's say, 7 approaches, close approaches, and the things kept working, kept functioning. So there's some pretty smart people out there.
They often have to shut it down during the closest approach to prevent the overheating happening.
Ah, okay. That makes sense. Right, yeah. Sometimes they didn't say that in any of the presentations, but that wouldn't surprise me at all.
Some of the satellites have had to do that.
Yeah, I don't think Parker Solar Probe has to.
Right.
No, its whole deal is getting as close to the sun and observing as it can get.
That maelstrom, yeah.
Last, you've got
You were saying they hadn't decided yet, or there wasn't how it was going to be like deorbited or whatever it is. Why is that? And is it going to like fall into the sun or
No, I think it's unpredictable. They're not able to predict what its ultimate demise is going to be. I think the mission will end 2025. They'll switch the thing off. Beyond that, what's going to happen?
We can give it more money.
They won't switch it off, but that's when the extending mission that they have at the moment runs out.
Right.
What's expected is that they'll have another extended mission phase, and they'll just keep.
They'll keep it alive. Okay.
Okay.
As so many NASA projects.
Yeah, that's true.
Way.
Yeah.
Well, look at Perseverance. And the opportunity is still going.
Yeah.
Yeah.
Is anyone at home asking a question?
I can't see.
Any of the chat?
Notionally, people put their hands up, you know, there's an interface that lets you do that.
Yeah.
I can't see anything. I think that anyway, we've got to actually do the last. That's going to take about 15. So this is a recorded one. So we need to get out here by 9, I believe. That's the.
So time's now about 8:30.
That's fine. 8:30. We need to. Okay, so I'm just going to get this queued up. And this was actually recorded last month. Scott Marshall's actually on a humanitarian mission in Cambodia at the moment. I think he's working with the medical team or something to help him out. So he's got a very nice, oh, that's the way Scott is, very helpful. So we've got a talk that he's done a little while back, and I've recorded it. So it's just going.
He's doing humanitarian work in Cambodia.
Yeah, that's what he's doing. Yeah. So what I'm going to do is get this thing shared, and then I'll.
Oh, there you go.
Yeah, what I'm getting to.
You have the technology.
Just got to try and maximise the screen though.
I think it's on the little bar. It's the third one from the right, that one.
The green dot.
Yeah.
Isn't it that one? Go back to the bar, the third one from the right.
Yeah.
No.
No, a little bit, I mean the small bar.
That thing that you.
The thing that climbed up at the bottom, I think.
Yeah.
that's what-
There.
The
Okay.
third one from the right.
Click the triangle.
No, go, third one on the right.
You know, back.
I'm not, I don't get it. I'm sorry.
Well, because you're looking at the screen in front of you and not the one that we can see.
Well,
That's
that's fine because I can't see that. Anyway, let's just.
Okay, that'll work.
So tonight's remote presentation from Scott Marshall, which is actually overseas, is the resolution of commercial and military satellites. Take it away, Scott.
Well, thank you, Wayne, and thanks for the opportunity to give this talk. The purpose of this brief talk is to reveal the image resolution of commercial and military satellites and to look at a bit of the history of satellite capabilities. Most of the urban areas you see in Google Maps or similar services, the images may not be from a satellite, but rather from an aircraft. Generally speaking, in the high resolution images on Google Maps, where you can see which way a tower is facing, was sourced from an aircraft-based photography. Some of the history, I'll just go back very, very quickly. There are a lot of satellites that have been launched since the 1960s, and they have been code-named with names such as Corona, Argon, and Lanyard. These images were declassified in 1995 by a presidential executive order. For a lot of these satellites, they had the designation keyhole or KH, and I have here the KH designations for the Corona, Argon, and Lanyard satellites, spy satellites. You might remember from an earlier talk that I gave, the shell of the Hubble Space Telescope is actually the shell of one of these keyhole spy satellites. A bit of interesting history with imaging from the spy satellites. One of the KH-11 satellites operated by the NRO, which is a spy organisation in the United States, was used to scan the underside of Columbia's first mission, which was piloted by John Young while in orbit. This was planned over a 6-month period prior to launch, and only a few of the NASA personnel were aware of this part of Columbia's mission. For more details on this, there's an excellent article called SpySat and the Shuttle, dated 2017, which gives you details of the reason for this view of the Columbia Space Shuttle and the work and engineering requirements to get this to work so that shuttle was located close to that spy satellite and oriented in the right direction. There's a group of satellites called the Hexagon spy satellites. There's 20 satellites in this group. They were operated in the 1970s. They may have had at the time a better resolution that is currently available on Google Earth. They were the size of a bus and had a very large mirror. So back in the 1970s, it is believed that spy satellites had pretty good imagery. In general, the images from satellites are classified into 3 groupings. They are the low resolution grouping, which has a resolution of 6 meters to 2 kilometers per pixel. Medium resolution from 10 meters to 30 meters in general per pixel, and the high to very high resolution, with resolutions in the 30 centimeter to 5 meter band. I've got here a list of commercial satellites. These are relatively early commercial satellites and the image resolutions for each one of them. You can see here the Landsat satellites, which were commissioned around the period 1972, had a resolution of 60 meters up to 120 meters for different spectral bands within the satellite. The Spot, which is a French satellite launched around 1986, had a resolution down to 1 to 2 meters. The NOAA meteorology satellites in the United States, which were launched over a long period of time from the 1970s to the 1990s, had resolutions in roughly the 1 kilometre up to 14 kilometre range. Now, the reason this was a very coarse resolution was, of course, these were for weather systems, looking at clouds, etc. So it wasn't important to be able to see a car or a person if you're looking at clouds. And there was also the NASA ER2 satellites, which had a resolution down to 11 meters, but this was imagery taken from aircraft, not from satellites, in, again, the 1970s. So those resolutions look kind of okay, but when we look at modern resolutions, they are really crude resolutions. Then when you look at the extreme end of resolutions that we believe are available from spy satellites, we believe that spy satellites have a resolution of around 5 centimeters per pixel. That's according to a tech expert, Noria Khan. And at this resolution, you could make out 2 men sitting at a bus stop, for instance. It is also believed, although it's not been proven, that you can get resolution in spy satellites down to 1 centimetre. It's believed that's used by advanced government spy satellites. At this resolution, you can see clothing details, cracks in a sidewalk, and small bits of trash on the ground. And this information was sourced from a website, www.cnet.com, which is a fairly reliable website, and that's dated 2024. So potentially down to 1 centimetre, but it's not verified. So as I say here, the resolution of the spy satellites is not accurately known, it's theorised. For commercial satellites, the resolution of the satellites can these days go down to 15 centimetres, but you're not allowed to publish that resolution. For various regulatory reasons, principally from the 3 United States departments that are listed here, you're not allowed to publish publicly a resolution less than 30 centimetres, even though satellites can operate down to around 15 centimetres. If you were to publish an image of less than 30 centimetres, in general, there is an exception coming up, you can only publish that to the defence departments. There's a commercial satellite company which publishes not only its own, but images from a number of other organisations. And their resolution is down to 25 centimetres. And with what's known as synthetic aperture radar technology, their satellites can give you images down to 16 centimetres per pixel. Now, at the moment, the NOAA has temporarily relaxed some of its regulations. So right at the moment, you can sell images down to 16 centimetres publicly, but it's not known how long that window of opportunity will stay open. You can obtain from the Umbra database and a number of other databases around the world today images down to 16 centimetre resolution, but normally 30 centimetre resolution for only a few dollars, typically $5 per image. So these images are effectively free to the public. I'm going to show now very quickly an example of an actual classified military spy satellite image. This image was of a Iranian launch site, and President Trump showed this image of a classified launch site in 2019. It's apparently taken from a spy satellite, hasn't been confirmed. It was initially believed that the photo was taken by a drone in the area, but when you look at the time of day and the shadows, there was actually a spy satellite in the right place to take this image. And this is the image, we believe, from a US spy satellite. This image is, quote, much higher than anything that the Federation of American Scientists believed was possible at the time. Now, when you look at the resolution of satellites in general, there are two things that can increase the resolution. One is by the use of synthetic aperture radar, and I'll mention what that is in a second. And the other one is by having faster revisits of satellites to that location, i.e. having more satellites to produce a higher volume of high resolution images. We can expect any part of Earth to be revisited by a satellite several times per day within a few years. Now, the synthetic aperture radar is an interesting piece of technology where basically you emit a radar pulse from a satellite, and as the platform, as the satellite moves in space, it has the effect of the dish being larger than the actual dish on the satellite because it is moving in real time while the radar pulse is being directed to Earth, bouncing back and being received again. So you can imagine a 1 meter, for instance, platform, radar dish, effectively coming 1.5 meters or larger because of that time delay. And hence the resolution improves because you have effectively a larger radar dish. Now, when this technology, synthetic aperture radar, becomes available on commercial satellites, satellite image data will be ubiquitous and cheap. It won't be long before we'll be able to take out our mobile phone and say, show me this morning's soil moisture map for Centennial Park. I want to see if I can have a picnic in the park with friends today. So in a few years, that is what we'll be able to do with your mobile phone, linked to these high-resolution SAR commercial satellites. Thank you very much. That's the end of the presentation. I hope you found it enjoyable.
That's excellent. Elizabeth, you got anything you want to ask?
Not so much a question, but just a comment on how absolutely thrilling. And I'm just wondering what impact this will have, you know, for our privacy issues and like as in Big Brother is watching you, you know, and how far will they, how can this be controlled, you know, with the privacy issues? Could it be, if it falls in the wrong hands, could it be used?
Sunbathing in the backyard.
Yeah, I don't want them to see me because like, this is what it's being wanting to use here. I mean, that is absolutely, you know, amazing to think of the resolution.
Well, there's a couple of answers there. First of all, with the spy satellites, the resolution, we can be relatively certain that spy satellites are down to 5 centimetre resolution. That 1 centimetre I mentioned, that's theorised. It may be possible, but that'll be from a low Earth orbit satellite because your resolution is a function of the height of the satellite as much as anything else. But yes, if you wanted to look at things as a military person, you've got a lot of detail. On the commercial side, if you were operating a satellite registered in the United States, in a normal environment, you're limited to 30 centimetre resolution. It's not operating today, but that's normal. So 30 centimetres, you can see a lot, but you can't see an individual per se. If you were in a totalitarian regime, that all changes. Yeah, that all changes.
threaded or thing on.
So yes, it is an issue. You would have enormous data sets that would have to be analysed to be able to make use of that data, but that won't be an issue either. Yeah.
I was going to make one quick comment. I believe that you were talking about objects of the size of the bus in the 1990s. Did you remember ever hearing about the story, what happened with the Hubble Space Telescope when the US military decided to give NASA some spare parts? It would appear that the military did have some satellites that were similar to the Hubble Space Telescope, except pointing the opposite direction.
That's absolutely true.
Okay,
I did say very, very briefly that the shell of the Hubble is actually a spy satellite shell. And yes, you're right. All they did is they flipped it around so it points to Earth instead of into space. To give you an idea of the sorts of technology the Defence Department might have, we are very, very familiar with the Apollo astronauts with hand cameras and taking videos on the moon, black and white videos on the moon. They only got access to that because the NASA went to the president at the time and said, we believe the Defence Department has basically a picture tube of the guts of the camera, which is handheld. At the time, cameras of that quality were what you used to see rolling around the Channel 9 studios on wheels. And NASA couldn't take one of those into space. So they wanted what the Department of Defence had. Yes, the Department of Defence had exactly that, some technology that they could collapse a Channel 9 studio camera down to a handheld device. That's Department of Defence technology compared to commercial. Now, do they have the same in spy satellites today? We don't know, but the expectation or the thought is that they do. Now, they are operating within physical limits, of course, as well. So we're talking about satellites, I presume, at low Earth orbit to get that high resolution.
Yes, it's fascinating and worth thinking about, and I think it's. I thank you for giving us this talk for that reason, because it's made everybody think about imagery and what we can do and what we can't do, and what we might be able to do, depending on how friendly everybody is, I suppose, and trustworthy. I think is the other word, trustworthy.
Yeah, well, there's a couple of things there. I mean, I've left this slide showing here. Very soon you'll be able to link your iPhone to really, really great imagery technology. If it's $5 an image today, it'll be far less in a couple of years' time. So you will be able to do this sort of thing now. Soil moisture, okay, that's a bad example. But you'll be able to do all sorts of things with this high resolution capability on your phone and do various analysis. I mean, Apple will come up with all sorts of great ideas what to do with it on your phone. So it's going to be an interesting world.
Sure. Yeah, thanks very much for talking about it, Scott, and I'm sure all the others will look forward to listening to it.
Thank you very much.
That was an excellent talk by Scott too.